students, greetings of the day. In the last session, I had discussed about two kinds of modulus of elasticities. One was Young's modulus and the other was shear modulus. In this session, I am going to discuss about one more kind of modulus of elasticity, that is bulk modulus of elasticity. Also, we will see a lot number of questions based on these all modulus of elasticities. So, shall we start now? Already we have discussed two types of modulus of elasticity. One was Young's modulus of elasticity and the second was shear modulus of elasticity. Now this is the third and the last one, which is bulk modulus of elasticity. What is bulk modulus of elasticity? Let us consider a situation here. If in a beaker some water is filled and inside a block is there, so of course it will be uniformly compressed from all sides, and then due to this compression it will undergo a decrease in volume. As you can see here, if it is a block of this cubical shape, forces will be from the water from all the directions perpendicular to all the faces. So this kind of forces are called compressive forces, and this lead to decrement in volume of the block. Now if there is delta V change in the volume, originally if it was equal to V, then we can write that this compressive pressure has to be proportional to delta V by V. And from the definition of modulus of elasticity, if we replace this by an equal to sign, then it has to be one proportionality constant involved. This proportionality constant is called bulk modulus of rigidity. But this time, since the forces are compressive, the stress is compressive, so one minus sign has to be put here, because always when compressive forces are there, there will be a decrement in volume. So delta V has to be negative, and to make it positive, we have to write minus delta V by V. So now we can write B to be equal to P upon minus delta V by V. This is called bulk modulus of elasticity. One another term is there. This is also very commonly used while dealing with compression, that is called compressibility. So compressibility is nothing but it is simply reciprocal of the bulk modulus of elasticity. Generally it is represented by C. So we can write C to be equal 1 by B. This is the term compressibility. Its unit has to be, as for bulk modulus of elasticity, it will be having unit Pascal, so it has to be Pascal inverse. Now bulk modulus of solids, if we compare with that of liquid and gas, then bulk modulus of solid is at least 50 times that of liquid, and for gases it is 10 to the power minus 8 times that of solid. So we can quote this: B of solid is greater than B of liquid, which in turn is greater than B of gases. We denote bulk modulus of elasticity with K also, and isothermal modulus of elasticity of gas can be written as, for gases, this value either we can write B or K, its value is equal to pressure of the gas. But this is only for isothermal processes. If the process is adiabatic, then for gas, this K can be written as gamma times P. We will see this later also in coming sessions. Till then, you have to simply memorize this value. So if a question comes which is having use of this formula, we can make use of it. Now here one thing has to be noted. Bulk modulus cannot be taken as the measurement of elasticity, because if a material is having large bulk modulus, it will be difficult to compress, but it does not need to be stiff. Let us take example of water. Water is very difficult to compress, but of course this is not stiff, it is a flowing material. So here we cannot exactly consider bulk modulus as the measurement of elasticity, which can be done for Young's modulus and for shear modulus of elasticity. Now let us take some illustrations based on this bulk modulus of elasticity. The first one is calculate the density of water near the bottom of the ocean where pressure is about 500 atmosphere and density of water is 1025 kg per meter cube approximately. Take bulk modulus of water as 2 into 10 to the power 9 Newton per meter square. Now if we have to write from the formula, delta V can be written as delta P multiplied with V upon K. Now here pressure change delta P is, this is 500 atmosphere, but we have to write the change in pressure. So delta P has to be equal to, this will be 500 atmosphere minus the atmospheric pressure which is 1 atmosphere. So this will be 499 atmosphere. Generally students do this mistake while putting the value of delta P. Whatever is pressure given there in the question, they do write the same value for change in pressure also. Always you have to subtract atmospheric pressure or the surrounding pressure from the given value of pressure. So here we got delta P to be equal to 499 atmosphere. And if now I substitute all the values, delta V will be 499 into 10 to the power 5 into 1 upon 2 into 10 to the power 9. So this value will be equal to 0.025 meter cube. So this is the change in volume. But it is asking for density. So let us write the density. It has to be mass upon the volume. And what will be volume? Volume has to be the original volume minus the decrement. So this is V minus delta V. And that can be written as, for 1 meter cube, if I write, this value will be 1025 upon 1 minus 0.025. So the answer is 1051 kg per meter cube, which is the density at the depth where pressure has become 500 atmosphere. So density also varies with depth or with height. The next illustration is a hydraulic press contains 0.25 meter cube of oil. Find the decrease in volume of oil when it is subjected to a pressure increase, that is 1.6 into 10 to the power 7 Pascal. The bulk modulus of the oil is given here. We have to calculate decrease in volume of oil. B, as you know, can be written as delta P upon delta V by V. One minus sign has to be put here. So if I substitute all the numerical values, this will be 0.25 into 1.6 into 10 to the power 7 Pascal. Here directly pressure increment is given, so it can be directly put in the formula. Then it has to be 5 into 10 to the power 9. On solving this all value, we will get this to be equal to minus 8 into 10 to the power minus 4 meter cube. And so we can say that decrement in volume is equal to 8 into 10 to the power minus 4 meter cube. If now I have to calculate the fractional change, the percentage decrement, so then it can be written as, it will be delta V by V, and this value will be 8 into 10 to the power minus 4 upon the initial value, that is 0.25. So on solving this, it has to be multiplied with 100 to get the value in percentage. So it will be equal to 0.32%. But do remember, this is the decrement. So one minus sign has to be put here and here as well. One more question is there. Compressibility of water is 5 into 10 to the power minus 10 meters square per Newton. Find the decrease in volume of 100 ml of water when subjected to a pressure of 15 megapascal. Here we know that compressibility is reciprocal of bulk modulus. So directly we can write delta V to be equal to, it has to be minus V into K into delta P. Now simply substitute all the values. This will be minus 100 ml multiplied with 5 into 10 to the power minus 10 into 15 into 10 to the power 6. So this will be minus 0.75 ml. This is the decrement in volume, which is equal to 0.75 ml. The next one, the bulk modulus of rubber is 9.8 into 10 to the power 8 Newton per meter square. To what depth a rubber ball be taken so that its volume is decreased by 0.1%. As we know, bulk modulus B can be written as it has to be delta P multiplied with V upon delta V. So from here we can write delta P to be equal to B delta V upon V. Let us now substitute the values. Now at depth H, the density of water, if it is rho, then we can write delta P to be equal to H rho G. So H rho G will be equal to B delta V upon V. From here we got H to be equal to B delta V upon rho GV. On substituting all the numerical values, it will come out to be 100 meter. So if we go inside the water by 100 meter, the volume will be decreased by this much for the given rubber ball. So if a rubber ball is taken inside the water by a depth of 100 meter, its volume will be decreased by 0.1%. Now I am going to discuss about what is the analogy of rod as a spring. Can we consider during solving the numericals that rod behaves like it is a spring? Of course, if we consider the property of elasticity, behavior of rod can be thought of as being that of a spring. So here I am going to see the analogy between these two. A thin wire can be imagined as a parallel combination of arrays of molecular springs. When we pull a wire, we really pull the springs. Let us take an elastic rod of length L, area of cross section A, and modulus of elasticity Y. So let us draw this situation here. Length is given, area of cross section is given, and Y is given. Now if it is to be pulled by some force F, then the rod will elongate under the action of this force, and we have to write as Y can be written as stress by strain, so it will be FL upon A delta L. And from here we can write F to be equal to AY by L into delta L. What kind of force this is? As we know that this has to be constant for a given wire, so we can write that F is proportional to change in length. Do we get the same kind of force for spring also? Yes, we write the same kind of force where for spring also, where F can be written as proportional to the extension in length of spring, and if it is to be replaced by an equal to sign, one proportionality constant that is known as spring constant comes into picture. What is this value? We can imagine that these two are similar terms. So now we can consider an elastic rod to be behaving like a spring, where spring constant can be written as equal to AY upon L. So it is a spring constant of which depends on area of cross section and the length of wire and its modulus of elasticity. This kind of model can be used to solve the questions. Now as the rod behaves like a spring, so of course we can consider for a combination of wire as combination of spring also. Let us consider those combinations. If we take this series combination, so one wire being attached to another in this manner. If lengths are L1, L2, area of cross section A1 and A2, and Young's modulus as Y1 and Y2, then we can consider that this will behave like two springs. We are connected like this, where they are having spring constants K1 and K2. And as we know that if two springs are connected in series, then we can replace these two springs with an equivalent spring, where K equivalent can be written as K1 K2 upon K1 plus K2. So the given combination of wire can be replaced by this spring model, where K equivalent will be having this much of value. Of course, we have to write K1 to be equal to A1 Y1 upon L1 and K2 to be equal to A2 Y2 upon L2. Then we can replace this whole combination with a single spring having this much of spring constant, and then can solve our numerical. Let us take one illustration now. A steel bar ABCD, which is of 40 cm length, is made up of three parts AB, BC and CD. The rod is subjected to a pull of 25 kN. As it is shown here, find the total extension of the rod. Young's modulus for steel is having value 2 into 10 to the power 11. I am writing for AB, so it will be F upon area of AB. This will be having value equal to 25,000 upon its area, which is square of 50. That will be equal to 12.73 Newton per millimeter square. And similarly, we can write stress for part BC. This will be F upon area of BC. Its value will be 25,000 upon pi by 4, because it is a circular one, you can see here. This will be pi by 4 into square of 25. And this answer will be 50.93 Newton per millimeter square. And in the same way, we can write for part CD, it has to be F upon area of CD, which is having value. On putting all numerical values, we will get 12.73 Newton per mm square. So these are the stress in the three parts. Now we can write total extension of rod should be equal to extension in part AB plus extension in part BC plus extension in part CD. So this will be, already we have calculated the stress, so it has to be 12.73 upon 2 into 10 to the power 5 into 10. This whole multiplied with 2 plus 50.93 upon 2 into 10 to the power 5 into 200. This answer will be 12732 upon 2 into 10 to the power 5 mm, which on further solving will give 0.0637 mm. So this will be the total extension in the rod. Let us do one more question. Three elastic wires PQ, PR and PS support a body P of mass M as shown in the figure. The wires are of same material and cross-sectional area, the middle one being vertical. Find the load carried by the middle wire. Let us consider the extension in these wires. So if it is the previous situation which is shown here, then of course due to hanging it will extend by a little, the whole arrangement will extend by a little. So let us draw that new arrangement when the wires have been extended. It will be like this. Now the mass has come here. What will be the extension in the wires QP and PS? It has to be by these values, because if I draw perpendicular on these wires, these will be the values of extension. Here I am writing this value to be delta L2, while for middle wire this extension is equal to delta L1. The weight of course is mg, as obvious from the given situation. Now tension, if we consider, has to be T1 and T2, and both being symmetric must be same. Now if we consider tension in these three wires to be equal to T1, T2 and T3, then we can write for horizontal equilibrium of point P, T1 sin theta should be equal to T3 sin theta, and that will lead, because these are the symmetric conditions, so we can write T1 to be equal to T3. Also, if we write vertical equilibrium, then that will be T2 plus 2t cos theta should be equal to mg. And if delta 1 and delta 2 are the elongations in the middle and the side wires, then we can write delta L2 to be equal to delta L1 cos theta, which is obvious from this diagram itself. So now we can write T by Ay A sec theta to be equal to T2 by Ay A cos theta. And from here the result will be T being equal to T2 cos square theta. Now if I solve all these equations, finally I will get T2 to be equal to mg upon 1 plus 2 cos square theta. T1 to be equal to T3 to be equal to T, and that being equal to mg cos square theta upon 1 plus 2 cos cube theta. So these are the tension in the different rods. Here it was asked only for middle wire, that is the tension T2. But for the clarification, I have calculated even tension in these two side wires also. One more thing is there, that is bars of composite section. What if the whole bar is not made up of a single material? It is made up of two materials, and you will see later that this kind of bars is generally used in construction. These bars are called composite bars. So let us consider one simplest case where this is a kind of composite bar, a cylindrical bar I am showing here, where the inner area of cross section is A1, the outer one is A2. If F is the force applied like this, which is the normal force, and length of the bar is L. Here this column I have considered, it is made up of two different material. The inner section, which is having area A1, is made up of a material of Young's modulus Y1. So for this inner one, Young's modulus of material is Y1. For the outer one, it is of Young's modulus Y2. Now if sigma 1 and sigma 2 be the stresses induced in the two materials, then sum of restoring forces in the two materials should balance the externally applied load F. Or we can write that if compression in two portions have to be same, so then sigma 1 upon Y1 should be equal to sigma 2 upon Y2. Also we can write sigma 1 A1 plus sigma 2 A2, that has to be equal to the net force applied on the composite bar, because these will be the stress multiplied with area of inner bar, sigma 2 A2 being the force applied on outer bar. So on adding these two, we will get the net force F. Now if I solve these two equations 1 and 2, we can write sigma 1 will be equal to Fy1 upon A1 Y1 plus A2 Y2, and load supported by outer section F2 can be written as sigma 2 A2, that will be having value Fy2 A2 upon A1 Y1 plus A2 Y2. If I generalize above formula, the loads borne by different portions will be, it has to be F will be common for all. So F Y1 A1 upon summation of AI YI. If a number of material are there, so that the composite bar is made up of a number of materials, we can generalize the formula. Load borne by each bar will be having this value. That is Fy1 A1 upon summation of Ai Yi, where I will go from 1 to the number of material that are there in the composite bar system. With this, our today's session is complete. Keep safe, keep masked. Goodbye.